Hello everyone, I'm Professor Harrison and welcome back to our module on regression analysis. Today we're going to be covering heteroskedasticity. It's a real mouthful of a word, but it's a pretty intuitive idea, and it's one of the most common issues you'll run into with real financial data. We'll cover what it is, what it does to your results and how to spot it, and the standard modern fix for it. We're following Margot, a graduate student trying to reassemble a story her family buried. Today's question is, what happens when the spread of your data isn't the same all the way across? When some parts of your regression are a lot noisier than others. She turns to the next problem in her coursework. So to understand heteroskedasticity, it helps to remember one of the classical assumptions we made way back when we set up OLS. One of those assumptions was homoskedasticity. That's the idea that the error term has the same variance for every observation. The spread of the errors is constant all the way across the data. Heteroskedasticity is simply the violation of that. It's when the variance of the error term changes depending on where you are in the data. Some observations end up tightly clustered around the regression line, and others are really spread out. And this isn't some rare edge case. It's everywhere in cross-sectional finance data. The classic reason is that variance tends to scale with size. So let's make this concrete. Let's say that Margot is looking at executive compensation across a few hundred public companies, and she wants to know whether bigger firms pay their executives more. So the goal is to see how pay relates to firm size, which means we regress executive compensation on the size of the firm, measured by something like market value. Now think about what the data actually looks like. Take the small firms first. A small company is pretty constrained in what it can actually pay. There just isn't that much money to go around. So among small firms, executive pay clusters pretty tightly. The actual pay numbers land close to whatever the regression line predicts, and the errors are pretty small. But now let's look at big firms. A giant company might pay its CEO a fairly modest package, or it might pay an enormous one. There's a huge range. Some pay conservatively, some pay out gigantic packages loaded with stock. So among the big firms, the actual pay is all over the place relative to the line. The errors are very large. So the spread of the errors grows as firm size grows. Small firms it's tight, but big firms is really wide. If you plotted the residuals against firm size, you'd see a shape that fans out as you move to the right, kind of like a megaphone or a funnel opening up. That fan shape is the visual signature of heteroskedasticity, and it's the first thing to look for. Okay, so why do we care? What does this actually break? And here's the good news first, it doesn't actually bias your coefficients. Just like with the issue we saw last time, the OLS estimates stay unbiased and consistent. The slope and intercept are still centered around the truth. So Margot's estimate of how pay relates to size is still perfectly fine. The problem is in the standard errors. The standard error formulas that OLS uses are built on the assumption that the variance is constant. That was the homoskedasticity assumption. When that assumption is false, those formulas hand you the wrong standard errors. And the standard errors are what everything else is built on. Your t-statistics use them, your p-values use them, your confidence intervals use them. So if the standard errors are wrong, then your t-statistics, p-values, and confidence intervals are all wrong too. You could look at a coefficient and conclude it's strongly significant when it really isn't. Or the other way around. The coefficient is right. The story you tell about its significance is unreliable, though. So how do we detect it beyond eyeballing the residual plot? Well, there's a couple of formal tests. The most common are the Breusch-Pagan test and the White test. You don't need the full machinery right now, but the idea behind both is the same. They take the squared residuals, which are basically a stand-in for the variance at each plot, and they check whether those squared residuals are related to your predictors. If the variance were truly consistent, there'd be no relationship. The null hypothesis for these tests is that the variance is constant. In other words, there's no heteroskedasticity. So if you get a small p-value, then you reject the null and conclude that you do have heteroskedasticity. The White test is just a more general version that also looks at squares and cross products of the predictors, so it can catch more patterns. So suppose that the test confirms it. How do we fix it? This is the nice part. The modern fix is almost free, and it's basically what everyone does in applied work now. You switch to what are called robust standard errors. The full name is heteroskedasticity-consistent standard errors, and you'll also hear them called White standard errors or uber-White standard errors, after the people who developed them. And the good news is that switching to these is pretty easy within any code or way that you run a regression nowadays. The key thing to understand, though, is what they do and don't change. They do not touch your coefficients, and they shouldn't because the coefficients were already unbiased. There was never anything wrong with them. What robust standard errors do is recompute the standard errors in a way that doesn't assume constant variance. Instead of pretending that the spread is the same everywhere, They use the actual squared residuals at each point to figure out the real uncertainty. So you end up with standard errors that are valid even when the variance changes across your observations. And once your standard errors are truly trustworthy again, then your t-statistics and confidence intervals mean what they're supposed to mean. In most statistical software, this is just a setting you can easily turn on. So when Margot is working on firms with wildly different sizes, she basically reaches for the robust standard errors by default. Margot files this one away as a habit more than a result. Almost everything in her investigation involves comparing firms and funds of very different sizes, and that's exactly the situation where the error spread isn't constant. So from here on, before she trusts a single t-statistic in any of that work, she's going to be running with robust standard errors. So that's heteroskedasticity. The whole idea is that when the variance of the errors isn't constant across your data, your coefficients are still fine, but your standard errors will lie to you. And since the standard errors drive t-statistics, p-values, and confidence intervals, all of your inference becomes untrustworthy. You spot it with a fan-shaped residual plot or a formal test like the Breusch-Pagan or White test, and you fix it by switching to robust standard errors so your conclusions can actually hold up.